Hello everyone, this is 11.1, which is a section on sequences. This is a very intro section, so I'm not going to talk too much about a lot of the details. I'll just introduce the notation and some of the language throughout the section. That's really it. So here I say a sequence is a list of numbers in a specific order, so usually it's A1, A2, A3, and so on, and we label it as A sub n in brackets like this, or braces like this. So, for example, if we have a general term A sub n equals n over n squared plus 1, we can write the sequence by just plugging in numbers. So basically this A sub n is a function, but only when we plug in natural numbers, meaning 1, 2, 3, and so on, so positive whole numbers. So for example, when n is equal to 1, n is equal to 2, and n is equal to 3, we can actually write each of the terms. So when n is equal to 1, we have 1 over 2. Here we'll get 2 over 5. 2 over 2 squared plus 1 is 2 over 5. This can be 3 over 10. 3 squared is 9, plus 1 is 10. And then let's just do one more for n equals 4. So it's going to be 4 over 4 squared is 16, plus 1 is 17. So this is the sequence associated with this general term. So I didn't even say what to write in this example. I'm just giving you an example of giving a general term, we can find the sequence. Now, vice versa, given a sequence, we can actually try to find the general term. It's actually not always one-to-one, though. So, in fact, since a sequence is a very broad statement, you can actually just pick random numbers and call that your sequence, and there's no rhyme or reason to what the terms are. There may be ways of finding the general term, but not always, is basically what I'm trying to say. Now, in this case, what we're going to do is we're going to try to find a relationship between the order the numbers come in and each part of the fraction in this case. And you'll see there's some patterns that I'm going to pick up on that are very key in this section and all of chapter 11, in fact. So this will be the first n equals 1, second n equals 2, then n equals 3, n equals 4, and finally n equals 5. So something that I pick up on is that this is, for the fifth one sticks out because it's 5 and matches with 5. Now, I want that to be the case for the other ones. So the numerator should be 4, then 3, then 2, then 1. So for the odd numbers, it seems to work. 1, 3, 5. But for the evens, not so much. Maybe there's a way we can explain this, but even better, and maybe it's just because I already know the answer, but the denominator, 32, can be written actually as 2 to the 5th power. So this gives me some insight, actually. So I'm going to write this as 5 over 2 to the 5th. That's the 5th term. Now, the 4th term, can I write it as, can I write it like that? It's not obvious yet, so we'll skip that one. Now, for the 3rd one, we actually can write it like that because the denominator so happens to be 2 to the 3rd. And again, we'll skip the 2nd one. So I'm kind of going in a weird order here, but that's okay. And then here, this is 1 over 2 to the 1. So now just to show you in red, I'm going to emphasize on the fact that these numbers in red coincide exactly with the order that the numbers appear in, and they actually match basically the indexing of the sequence. So notice, the red 5s match with the index 5 up here, and the red 3s match with that 3, and the red 1s match with that 1. Good. So now, in order to make this work out, what should the denominators be for the ones I have not included? Well, this should be 2 to the 2, and this should be 2 to the 4. So let me just write that. It's fine. Okay. Now, of course, they're negative, so we'll deal with that shortly. Why exactly that happens is not really explainable yet, but you'll see there's a nice pattern to look out for. Now, the numerators, well, let's think for a second. So this is 1 over 2 to the 2nd, which is, well, not 1 over 2 to the 2nd, but something over 2 to the 2nd. 2 to the 2nd is 4. So 1 over 4 is equal to, this is 1 over 2. So this is 1 over 2, negative 1 over 2. But we're rewriting negative 1 over 2 as negative something over 2 squared. Now, right now I'm just ignoring the signs, just look at the fractions themselves. And notice, if the numerator is 2, then this actually works out. 2 over 4 is equal to 1 over 2. So now we can see the pattern is 1 over 2 to the 1, 2 over 2 to the 2, 3 over 2 to the 3, 4 over 2 to the 4. Let's see if that works. 2 to the 4th is 16, and 4 over 16 is indeed 1 over 4. So it seems to work out actually. So we have a good idea as far as what the fraction is, but the sign is still maybe throwing us off. So let me just write this to reassure us. So a sub n, the general term, is going to be, for the fraction part, the numerator is going to be the subscript n itself. So when n is 1, the numerator is 1. When n is 2, the numerator is 2. The denominator is going to be 2 to the n. Perfect. Now, the sign. Here's what we're going to, how we're going to handle the sign. And it's going to be a pretty, I guess, standard thing for us to recognize. It's going to be -1 to some power. Now, what the power is, we can check by plugging in numbers. But let me just say this. -1 to the nth power is -1 when n is even. Let me just write n even. Actually, when n is odd, my mistake. And +1 when n is even. There we go. That makes sense. Good. And you can verify that for yourself, but yeah. When you plug in n to be even, -1 to an even power is +1, -1 to an odd power is -1. So with that being said, we want this to be -1 to some power where the first one is positive. Since we're plugging in 1 for the first one, it can't just be n, because -1 to the 1 would be negative, but the first term is a negative, it's positive. So we can offset it by 1 by writing +1. So let me shift this over a bit. There we go. So this general term actually works for us. So we saw a lot of nice pattern recognitions in this example. The biggest one, I think, to end it was -1 to a power. -1 to a subscript power will actually alternate the signs. So now we're going to take a look at something else that kind of relates to this example, actually. Notice that in this problem, even though it kind of seems like the numbers go up and down like this and weave in and out, they actually get closer and closer to 0. So now we're going to take a look at certain types of sequences and categorize them by if their terms actually approach a number in the limit or not. Right, so here we say a sequence a sub n is convergent if its limit as n goes to infinity exists. Otherwise, it's called a divergent sequence. And L, by the way, is just called the limit of the sequence itself. So basically, it's what all the terms tend to approach as you go further and further out in the sequence. Okay, here all limit laws and properties are applicable, namely these. So if a sub n and b sub n are convergent sequences, then the following are true. Okay, so I have a few of these properties listed here. Now, you can take your time and read through them if you'd like, but it gets kind of more interesting as you go down to the last two. The limit of absolute value of a sequence is 0 implies that the limit of the sequence itself is 0, which helps because when you have alternating sequences, you can ignore the alternating part, and if it goes to 0, then that means with the alternating part, it still goes to 0. So that's nice. Here, this is if you have a continuous function for the last one. If you have a continuous function, you can pull the function out of the limit. So we'll see some examples of these, I think, right now. All right, so here I have 4 examples where I'm asking to find the limit of the sequence. And all we're going to do is take the limit as n goes to infinity and see if we can use some of the limit properties or laws that we've seen before, amongst other limit techniques, by the way, to figure out what the limit is and if it actually exists. So in this case, well, we're going to use that fact that I just showed you. So we're actually going to take the limit as n goes to infinity of the absolute value of the sequence. Now what that does for us is it actually gets rid of the alternating part. And if without the alternating part the sequence approaches 0, then that means that with the alternating part it actually approaches 0 as well. So that means now with absolute value we can ignore the alternating -1 to the n plus 1, and we just get this. Now as n goes to infinity, n over 2 to the n will actually go to 0 because 2 to the n gets larger and larger more quickly than n does. There are a few different ways of showing this. The best way I know to show it is by L'Hopital's rule, which we'll actually be seeing a little later in a few of these examples as well. So I don't mind showing you that, but the only thing is to apply L'Hopital's rule, technically you need x's instead of n's because it needs to be a continuous function so you can take its derivative. But that's a little technical. I'll still do it anyways though. So now we're going to take the limit as x goes to infinity of x over 2 to the x. And now we can take derivatives because it's a continuous variable x opposed to just a positive integer variable n. And now applying L'Hopital's rule, we can take the limit as x goes to infinity of derivative of the top, which is just 1, over derivative of the bottom, which is 2 to the x times ln of 2. And this indeed approaches 0 because the denominator approaches infinity and the top just stays 1. Now, if you don't remember L'Hopital's rule, basically you have to have an indeterminate form, either 0 over 0 or infinity over infinity. There are a few others, but I'll leave it to you to explore those on your own. But notice when we plug in infinity, we indeed get infinity on top, and 2 to the infinity would go to infinity for the denominator. So then we can just take derivative of top and bottom, leaving the limit part the same, and then try to plug in directly from there. So since with absolute value it goes to 0, that means the limit for part 1 is also 0. Perfect. Now for this one, there are a few ways of handling it. One way would be to use L'Hopital's rule. Notice derivative of top and bottom is 1, so this will actually go to 1. Another way of handling this, though, is like this. What you can do actually is you can add something to the top and subtract that same thing. So this is known as the mathematician's favorite trick. So if you add and subtract 1 from the top, what you end up getting is a scenario where you can actually split this fraction up as n plus 1 over n plus 1 minus 1 over n plus 1. And limit as n goes to infinity of that. There we go. And the reason why we like this is because the first one, of course, cancels and just gives you 1. And the limit as n goes to infinity of a constant is just a constant itself. So really the limit splits and we get 1 minus the limit as n goes to infinity of 1 over n plus 1. And we know this, of course, goes to 0 because the denominator gets closer to infinity where the top just stays 1. So the limit here is 1. So for the third part here, since sine is a continuous function, we can actually pull it outside of the limit. So that the limit as n goes to infinity of sine of pi over n is actually equal to sine of the limit as n goes to infinity of pi over n. Now, of course, since pi is a constant, we can pull that out of the limit and just get 1 over n. But regardless, you'll see the limit as n goes to infinity of 1 over n or pi to the n will each go to, will go to 0. And the reason there is because n, the denominator, will approach infinity where the top just stays pi. It's just a constant. Or again, if you pull pi out, you'll get pi times 0. It's still 0. So really this is just sine of 0, which goes to 0. So the limit here is 0. That's nice. Now this one is ln over n. Well, here I don't see any other way of doing it besides just L'Hopital's rule. So we need to have an understanding that, again, to apply L'Hopital's rule, technically, we need to change our n's to x's. Now the funny thing here is actually they're the same. The limits are the same. When you use x's instead of n's, it's not necessarily the same because x's implies you can plug in things like 1/2 or the square root of 3 or pi, any real number for that matter. N's only implies that you can plug in natural numbers like 1, 2, 3, 4, and 5, and so on. So now we can take derivatives because it's continuous. So now using L'Hopital's rule, because when you plug in infinity, ln of infinity is infinity, infinity in the bottom is infinity, so it is infinity over infinity indeterminate form. So the limit will stay the same, and then what do? We take derivative of the top, 1 over x, over derivative of the bottom, 1. That's just 1 over x, and as x goes to infinity, this of course approaches 0. So the limit here for this sequence is just 0. So in fact, all of these problems, even though they're in the context of sequences, are really just limit problems. We're still going to be talking about limits of sequences, but now we want to talk about particular types of sequences. So let's take a look at that right now. All right, so here we define this sequence r to the n, and we notice it actually has the following limit. So the limit as n goes to infinity of r to the n is 0 when r is in between -1 and 1, exclusive, so it can't be equal to those. It's equal to 1 when r is 1, which I think makes sense because 1 to the any power is 1. And it does not exist otherwise. So actually it is divergent here and convergent for these two, which is actually interesting. Now, I didn't really explain the other two, but for the top one, let me just try to explain this. So when r is less than 1, when the absolute value of r is less than 1, what you end up getting is a small number to a large power, and you can write the small number as a fraction where it's 1 over something. I will actually see that in this example because this is an example of that. So I'll try my best to explain that there. But that's the main idea here, is that if the absolute value of r is less than 1, then you can write it as 1 over a number that's bigger than 1, and then from there you can say as n goes to infinity, the denominator blows up to infinity, so you get 0 in the limit. Now otherwise it's kind of easy to explain. When r is negative 1, you get negative 1 to the nth power, and that just changes signs. It goes positive 1, negative 1, positive 1, negative 1, positive 1. So in the limit, it doesn't exist because there's no deciding factor which one it'll be. In fact, if you were to graph this, you just get like this ping-ponging effect, where you have one up here, then here, then here, then here, then here. There's no approaching at all. So that's what you get when you have negative 1 to the n. If you had negative 1/2 to the n, that's different. There is still this going back and forth, but now as we weave in and out, we'll actually approach something, and we approach 0. So that's kind of the difference here between actually having a limit and not having a limit. So not having a limit doesn't mean you always approach infinity or negative infinity. It could mean you just don't approach anything. So keep that in mind. Also, when r is bigger than 1, it blows up to infinity. When r is less than negative 1, like negative 2 for instance, that approaches positive and negative infinity, because not only does it ping pong back and forth, but it approaches infinity and negative infinity each time. So there are different ways of viewing that. But anyways, I'm going to erase this and move on to this example now. So here, to see that it actually is of this form, I'm going to manipulate it a little bit. So what I'm going to do is I'm going to write 3 to the n times 7 to the negative n as 3 to the n over 7 to the n, because of course a negative n power really means it's in the denominator. Then, since they're both to the nth power, we can actually write this as 3 over 7 to the n. And notice the base here is less than 1, so we have the idea that the limit should go to 0. And it does. It actually approaches 0. So I'll write that because we have this knowledge now. Now, but to show why that's the case, well, if you look at this, 3 to the n goes to infinity as n goes to infinity, so does 7 to the n. But 7 to the n approaches it a lot faster, approaches infinity much faster. So that means if you plug in n equals, let's say, 10, they'll both be really large numbers, but for sure 7 to the 10 is going to be way, 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 way larger than 3 to the 10. Then if you were to plug in numbers bigger than 10, well, the difference between the two would actually be even greater, meaning that the denominator approaches just infinity faster, so this whole limit would actually go to 0. Another thing we can do, which I was just trying to describe earlier, is we can actually write this as 1 over 7/3 to the n. And we know since the base is bigger than 1, in fact you can write this as, I guess, 2 1/3. Then 2 1/3 to large powers goes to infinity, so this approaches 1 over infinity, which approaches 0. So that's another way of seeing that. Anyway, so I've said enough about this. Now we're going to move on to talk about something else. So let's see that right now. Alright, so here I give a few definitions, and from there we have this final idea to finish this off for 11.1. So here I say a sequence is bounded above if there exists some number n, m, capital M, such that every term in the sequence is less than that number, and this for all n is bigger than or equal to 1 just means no matter what you plug into n, every term in that sequence will be indeed less than or equal to that number. On the other hand, a sequence is considered bounded below if there is some number lowercase m where all terms in the sequence are bigger than that number. So bounded above and bounded below just means there's either a cap or a minimum that the terms in the sequence could be. Okay. Beyond this, I say a sequence is monotonic if it is either purely increasing or purely decreasing. Now with these ideas combined, there's a visualization here, but I think it's kind of not too bad to see. I say any bounded monotonic sequence must be convergent, because bounded means that, well, I say bounded, I don't say if it's bounded above or bounded below, but bounded will imply that it's both bounded above and below. So let's say it's bounded above by m, and it's bounded below by m. So capital M and lowercase m. So this, of course, represents the n-axis, I guess. So we're going to be plugging different numbers in for n and seeing what the terms in the sequence will be approaching. Now, since we're bounded above and below by capital M and lowercase m respectively, then we can't go outside of our bounds. At the same time, if the sequence is monotonic, then it's either purely increasing or purely decreasing. So you see the issue here? So let's just say, for instance, it is increasing. If it is increasing and is bounded above by m, either the limit is m itself or it's some other number below m. But regardless, the limit would have to exist because all of the terms will be approaching some number because they continuously go up. So that's kind of the idea there behind sequence being monotonic and bounded. We'll see one example of that now, and that'll finish us up for this section. All right, so now for this example, this may be a little too intimidating, but I think we have the knowledge to do it. So just bear with me and let's see if we can figure it out together. We want to find the limit, if any, of this sequence a sub n defined by this recursive relationship here. So we have a starting value, a1 is 2, and then from there, we have a way to find all subsequent values by plugging in basically the previous value. So just to give you an example, we know a1 is 2, so a2, according to this, is 1/2 times a1 plus 6. Since we know a1 is 2, this is 2 plus 6, which is 8. 8 over 2 is 4, so a2 is 4. If you wanted to find a3, that's 1/2 of, well, 1/2 times the previous one, a2, which is 4, plus 6, so that's 10, so that's going to be 5. Then it gets a little more complicated because an a4 would then be 1/2 of 5 plus 6, which is 11, so that's going to be 11 over 2, which I guess is 5.5. So we can kind of see that the sequence seems to increase. We'll actually be showing that, but plugging in a few numbers, we can kind of get the idea that that's the case. Also, if you keep going, you'll see that all of the numbers will get closer and closer to 6, but still be less than 6. So I'm going to erase this and write those two claims down right now. All right, so the first claim here is that a sub n is monotonic increasing, so it's purely increasing. And the way we're going to show this is we're basically going to show that a sub n is less than or equal to, actually, I guess we could just say less than, purely less than, a sub n plus 1, the next term in the sequence. This is the way you actually would show that a sequence is increasing, that the next term would be larger than the previous term. Not or equal to, but strictly larger than. So the way I'm going to show this is actually by induction. So if you're not familiar with induction, basically we're going to show that it's true for a few cases, which we already did. Then we're going to assume that it's true for one case, and then from there show that it must be true for the next case. So basically what we want to do is we want to suppose that this is true for some n, for some natural number n. So we're assuming this is true. And now what I'm going to do is I'm going to manipulate each side with our recursive relationship, which I've erased since, but I'll write it here just to remind us. It was an plus 1 is equal to 1/2 times a sub n plus 6. So basically I'm going to add 6 to both sides and then multiply by 1/2. So when I do that, I'll get a sub n plus 6, a sub n plus 1 plus 6, like that. And then if we multiply both sides by 1/2, well, first off, on this side we just get a sub n plus 1. And on this side, this is just a sub n plus 2. So I know it doesn't seem like we've really done too much here, but honestly, this actually implies that a sub n is less than a sub n plus 1 for all natural numbers n. So basically we assumed it was true up to some number n, and then from there we actually get this, this implication that is true for the next integer in line. So namely, let's just say, for instance, let's say we assume it's true for 10. So this says that a10 is less than a11. Well, then doing this to both sides of the inequality, though it seems kind of simple, basically this implies that a11 must be less than a12. So what we end up getting is actually, if you keep doing this argument over and over, essentially what this shows is that it's true for all integers n. So no matter what the subscript is, it is actually true that a sub n is less than the next term in line, a sub n plus 1. So this first claim has been shown. Now the next claim, let me erase this and I'll write the next claim down. And that again was that they're all less than 6. All right, so now for this one, I'm gonna still apply actually induction. So the same kind of idea. So first off, the claim was that a sub n is bounded above by 6. So we're gonna start by supposing that a sub n is less than 6 for some positive integer n. And remember, bounded above technically meant that we're less than or equal to, but that's fine. We'll leave it like this. So we're assuming this is true for some n. We want to show that it's true for all n. So now we're going to take our induction step and, well, we're going to apply this recursive relationship to each side. Forgot to write the close bracket for the previous part, but that's fine. So I'm going to add 6 to both sides and then multiply by 1/2, and let's see what happens. When you add 6, you get this. Now this, of course, is equal to 12. And then when you hit it with the 1/2 multiplication, you get that this is less than or equal to half of 12, which is equal to 6. And the beauty of this is 1/2 times n a sub n plus 6 is just the next term a sub n plus 1, and that has to be less than or equal to 6 because of this line here. So this actually implies that this is true for all. Let me write it like this. This implies that a sub n is less than or equal to 6 for all n now. So I'm kind of oversimplifying the technique of induction. It's something you should kind of check out if you have time. Some of you probably have seen it before, others may not have seen it before. It's a pretty common technique improving things in mathematics. It won't really come up in this section at all, to be quite honest. I just kind of thought it'd be nice to do an example that involved something different. So that's why I'm doing it. So now, finally, our two claims imply what? Well, they imply that a sub n, the sequence, is bounded and monotonic. So this implies what? That the sequence is convergent. And it converges to 6 actually. Now the funny thing is we actually haven't shown that it approaches 6, we've only shown that a limit actually exists. If you want to actually show that the limit approaches 6, there's not too bad of a way of doing that using limit laws. And you know what? It's not going to take too long, so I'll actually show that right now. So let's just say it approaches L. Let me clean this up and I'll show that L must be equal to 6. All right, so now we have a third claim here that the limit is actually 6. So let's see. So since the limit exists from claim 1 and claim 2, it's monotonic and bounded, let's call it L, then we can actually say that the limit as n plus 1 goes to infinity, the limit is also L. So in other words, the sequence a sub n plus 1 will actually also approach L. So maybe there's a better way of writing that. The limit as n goes to infinity of a sub n plus 1 is L as well. Which makes sense because a sub n plus 1 is just the next term in line. In fact, basically these are the same terms as a sub n sequence, only shifted by 1. So the limit will still be the same. Okay, so now that we have that down, well, what is a sub n plus 1? So let me write this is equal to L. But what we know now is that a sub n plus 1 is what? A sub n plus 1 is, well, it's 1/2 a sub n plus 6, like this. And we can apply limit laws now to split up this limit accordingly. And in fact, we're going to split it up basically like this. 1/2 times limit of a sub n plus limit of 6. And the limits here, of course, go to infinity. Good. Now we know this guy is just L itself. So really we have, oh, well, also this is just 6 itself from that limit law of limit as n goes to infinity of a constant is just the constant itself. So really altogether, excluding these middlemen basically, we have the following equation. L is equal to 1/2 times L plus 6. So I think we're there. Just multiply both sides by 2, we get 2L is equal to L plus 6. And then subtract L to the left side and we get right away L is equal to 6. Great. So this actually shows that the limit must be 6. And like I said, that was really it for this section, 11.1. Thanks for watching. I really hope you enjoyed. I'll see you in the next video for 11.2. It's going to be a lot of fun. See you then.